All right, well, hi there. This is Mr. Kestel. I'm making this video to help you go through the first activity for science. If you look on the packets they gave out, that was about work and energy. So we're going to go through all the information covered in this packet. Now, what I'm not going to do is just go through page by page and tell you what the answers are. That would be silly. But I am going to go over the information and help you understand what the terms mean so you can fill out the paper yourself. And if you have questions after that, then you can get in contact with myself or Mr. Haggard. So let's get started. Okay, so the first thing we need to know is what the heck is energy? Energy is the ability to do change, cause some sort of change in something. So we're going to just say energy is the ability to cause change. So that could be lots of different types of changes, and we're going to look at a bunch of different examples, but energy is the ability to cause change. Also, it's measured, as hopefully you remembered, in joules. So sometimes it'll say like the SI unit, but joules is the unit of measurement. Just like when we measure time, we measure it in seconds, or if we measure distance, we measure it in meters. Now, I'm going to go through this based on the way that we sort of talked about it in class. This is not the way that this worksheet goes through it. So the worksheet jumps around between lots of different topics. I'm going to go through the topics and try to put all the information you need to know together. So the first thing that we want to know is, or the first type of energy we're going to talk about is potential energy. Now, and I'm working on typing quieter so it's not so loud. Potential energy, there's a couple different types of potential energy. The main type of potential energy they're talking about here is gravitational potential. So you can think of gravitational, oops, forgot to take that off. You can think of gravitational potential as the energy something has based on its height. So if I got a little rock up here on top of a ledge, it has the ability to fall. So the potential energy is based on the height. That was a wonderful straight line. The height and the mass of the object. How big is the object? So if we come back here, gravitational potential, and I'm just going to drop this down a second, is based on the height and mass of the object. Something to add to the potential energy here is that it is stored in an object. So for instance, we would say that this rock, the potential energy is stored in the rock. So again, so when you're talking about gravitational potential energy, that's based on the height and mass of the object. So I have a couple examples of the gravitational potential based on the height and the mass of the object. So if you remember this simulation from, some of you did this simulation in class, we've got a object hanging here, and as it swings back and forth, we looked at some different things. So I'm going to pause it when it gets up to the highest here, and if you notice, this bar over here, potential energy, is very high. And if it's not as high, if I lower it, then there's less potential energy. So it's depending on the height. And then also, if I make the mass bigger, then the potential energy goes up. And if I make the mass smaller, the potential energy goes down. I got another example here. Dude on a skateboard. the guy starts, or girl, if they start lower on the ramp, they have less potential energy. If they start up higher on the ramp, they have more potential energy. And also, if we have a small mass, they have a small potential energy. If they have a large mass, they have a large potential. So the second type of energy that we talked about was kinetic energy. Kinetic energy. Science teacher, not a spelling teacher. So hopefully remember that kinetic energy is the energy of motion. So if I have an object that is at rest, the object has no kinetic energy. So let's say this is a ball sitting on the floor. It has no kinetic energy, so it's not in motion. If something is moving, so let's just draw a ball here, and I'll draw little arrows to show that it's moving, then that has kinetic energy. So the kinetic energy is based on the motion of an object. So let's go ahead and type in that kinetic energy is the energy of motion. And we can say that is based on the mass and velocity of an object. This worksheet's not going to make you do anything with equations, but you know, Mr. Haggard and I like to make it trickier. So let's go back over to our skateboarder here. And once we have them start going down the ramp, they start moving faster, so their kinetic energy increases. And if we look at their speed, as their speed goes down, their kinetic energy went down. As their speed increases, notice what happens to the green bar. The green bar goes up. They're going faster. So their speed goes down, kinetic energy goes down. Their speed goes up, and kinetic energy goes up. And they're going the fastest at the bottom of the ramp, so that means that they have the most amount of kinetic energy. So what about, well, let me do this here. So let's get down to the bottom here. I'm going to pause it, and you can see how much kinetic energy they have. Now, what if their mass was smaller? Well, they'd still be going the same speed. Notice that as I move the mass, the speed doesn't change. Here, they went down the ramp, they are still going at the same speed, but making a smaller mass means you have smaller kinetic energy. Just like if I was running at you and Mr. Pink was running at you, Mr. Pink would have more kinetic energy because he has more mass. I'm skinny and Mr. Pink is very strong, so he would be able to push you over very easily and I would not. So that's what's going on with for kinetic energy. Again, it's based on the mass of the object and the velocity of the object. So more velocity equals more kinetic energy, and more mass means more kinetic energy, assuming it's going the same speed. So that will be up for kinetic energy. Okay, so there's a couple examples we need to examine when we look at kinetic energy and gravitational potential energy. So one of them is something up on a ledge. So this is a picture of a rock starting up on a ledge and then falling toward the ground. So when it's up at the top of the ledge, we would say it has a lot of EGP, or gravitational potential energy. And then as it falls, the kinetic energy, so EK, starts out small and then it gets bigger. So as the object falls, we get more kinetic energy. So I would draw, for instance, I'm going to draw this arrow to be much bigger because it's going much faster. Maybe a better example is the skater girl. So she's starting up at the top, and I'm going to increase the mass a little bit here. This potential energy, notice it's going to go down as and I'm pointing at my screen, but then I realized, oh, you can't see where I'm pointing. So I'll use the mouse arrow. As she goes down the ramp, the potential energy is going to decrease. At the same time, the kinetic energy increases. So let's watch. So potential energy decreases, kinetic energy increases. And then it goes back to where it was. So, let's write that down as a note that when an object falls, it converts gravitational, just making sure I am spelling things correctly, energy to kinetic energy. Okay? And the same thing happens on a swing. I don't have a swing, but I have a pendulum, which is a swing. So, well, that's going pretty daggone fast. First, I'm going to increase the mass here, so I'm going to slow it down. So as it goes down the swing, it gets faster, and so it has all kinetic energy. And at the top, it has potential energy. So the same thing is happening on a swing. Gravitational potential energy is converted to kinetic energy. So, same thing applies. Now, one other thing to point out is if you notice in both the skater and the swing here, the pendulum, the total kinetic energy stayed the same. And let's go back over here. Notice this yellow bar here, the total energy, in this case is just a matter of the kinetic energy and the potential energy. So those two are flipping back and forth. The total energy stays the same. So that total energy has a particular name, which is fine. We're going to call that mechanical energy. Mechanical energy. That just means that is energy due to position and motion. See, I spelled a word wrong. And so mechanical energy is equal to the potential, well, we'll say gravitational potential, plus the kinetic energy. Okay, so there's a couple places where it talks about mechanical energy. I think the term is kind of confusing, but whatever. I didn't make the worksheet, so I'm just trying to help you out with that. All right. So flipping back over to this worksheet here, there's going to be definitely things that I've already talked about that you could answer. There's lots of stuff that I have not yet talked about, which I will, but I just want to remind you that you can pause during this and try to fill out answers on this worksheet. The worksheets are based off of a textbook, and they're sort of review, so this is not necessarily a good worksheet for learning some information, because all the topics are mixed together. I'm trying to go through this and cover one topic at a time. So that's why there's going to be things here that you're like, hey, mister, you skipped talking about a simple machine, or what? Some of these different topics. We'll get to them, but I just want to make sure you understand how I'm going through the information. Okay, now we're going to go ahead and talk about some different types or ways that energy can be stored that the worksheet touches on. So, one of the types hopefully looks familiar, and apparently I cannot spell today, elastic potential energy, or it might just be called elastic energy. Hopefully that's familiar. That's energy when something stored in a spring. So if we have a spring that is really compressed, that's terrible, but that's all right. Versus if it normally looks like this, then this top one would be like compressed, pushing the ends together. And I really want to show that with my hands, but I can't. So, or the spring might be stretched and be a lot longer. So either case, there is elastic potential energy, EEL. So for the worksheet, it's basically just asking that elastic potential energy, that's the energy stored in a spring, and we'll include that that's compressed or stretched. All right. So that's the first type. Another type is chemical energy. We talked about this a little bit. Chemical energy, or chemical potential energy, I'll include the potential here. This is the energy stored in your food or chemicals, like gasoline. So, energy stored in foods, gasoline, and to be more specific, it's the energy that is stored in bonds between atoms. So what do I mean? If you've got, let's say we've got two hydrogen atoms. If you don't know about hydrogen, hydrogen likes to blow up if you light it on fire. So, or if you heat it up a lot. So the reason that happens is that this little line between the two circles represents a chemical bond. And that chemical bond is storing energy. It's kind of like a spring where it stores energy. It holds a lot of energy. And when you break that bond, it releases that energy. So by breaking, if we break that bond, so there's no more bond there, then both of those hydrogens have a lot more energy. So we're going to say that it is chemical energy is stored in bonds between individual atoms. Now, when we talk about energy stored in food, something that you may have seen, and I'm just going to Google this while I'm talking, is on a label, on a nutrition facts, you'll see something, calories. Here we go, calories. So calories are actually a unit of, a unit for energy. So, energy stored, well, we'll say energy from food is measured in calories. Okay, so there's a lot of stuff in we could go talk about with that you don't need to know. and I'm kind of generalizing. Anyway, calories is the unit for food. If energy is stored in food, we call it calories. Okay, so a couple more types of energy that we're going to talk about here. The next type is electric energy. This is hopefully something I assume you are familiar with, whether you realize it or not. You're using electric energy right now to watch this video. Energy. Electric energy is just the energy used to run all sorts of electrical devices. So we'll just say energy and electricity, and it runs electrical devices, including appliances. So your refrigerator, your toaster, all that kind of stuff. So, and then another type of energy is called radiation. This is energy given off as light. So of light, energy of light. So, for instance, plants use energy, radiation, to do photosynthesis. And how do I spell photosynthesis right, but I can't spell energy correctly? Whatever. So also, it's given off by the sun. The sun and by light bulbs. So anything, radiation, energies, any energy of light. And there's a lot of different types of radiation, which I think we'll talk about in a different video, but that's what radiation is. The last one we definitely talked about also, which is thermal energy. This is energy of heat. So, and so obviously the sun and light bulbs give off thermal energy. Also, it's energy, it can also come from friction. Friction force between two objects. So when two things rub together, they have friction between them, and we call that thermal energy. So we talked about that in a bunch of different circumstances. So those are all of the types of energy that we need to talk about. Okay, so there's basically two more big concepts that we need to talk about. The first concept is work. Work is when energy, again, I can't spell energy, when energy is transferred. So, work transfers energy. And so we talked about work as energy entering a system or leaving a system, and there's another way you can kind of talk about work. Work is force times a distance. So when you apply a force over a distance, you have work. So for instance, if you apply a force on the side of a chair, if you're pushing someone down the hallway and in a rolly chair, you're applying a force on the chair, that's work. there's a couple weird little things about this definition, but I'm just going to ignore those because I don't have to talk about them. So, work is really important when you talk about machines. So, work can be made easier by machines that multiply the force. So an example of that is a simple machine. So a simple machine is just something that that does work only one type of movement. So if you Google simple machines, we'll see some examples here. Oh, don't know what I'm doing. So a lever is a simple machine. An inclined plane, so something rolling down or rolling up a ramp is a simple machine. And a pulley, a wedge, these are all examples of simple machines. So they're a device that makes work easier. They multiply the amount of force. So for instance, this kind of has this picture right here with a guy pushing a box up a ramp. Pushing something up a ramp is easier than just lifting it straight up. You have to push over a longer distance, but you do not have to push with as much force. So that's why we use ramps to move stuff up and down. Another example of that is a pulley. A pulley can be used to lift an object. A wedge, going back to this picture, the force that you put in here to the top of the wedge can be used to split this log. An example of that would be like a boat hull. We talked about this a bunch. So the boat acts like a wedge, and it pushes the water to the left and to the right. It pushes the water out of the way. So, simple machine is a device that does work in one type of movement. So it does it in one movement only. Now, sometimes you can combine multiple simple machines. So that we call that a compound machine. So that's a device made of two or more simple machines. So going back to our Google here, an example of that would be like a wheelbarrow. A wheelbarrow has a wheel, obviously, and that is a simple machine. And then it also acts as a lever. So if you lift up with the handles, that is an example of a lever, and that it's a lot easier to lift with this than it is having to lift whatever's in the wheelbarrow itself. So if you have a big old rock in the wheelbarrow, you can lift it easier with the lever and then move it with the wheel than it is to just lift the rock by itself and move that. Another example is a bicycle. A bicycle has several wheels and axles, and by pushing on the axles, you can the pedals, you can move the bike, you can move faster. So for the same amount of force, you get more force out. So those are examples of simple machines or compound machines. So a couple words that I said as we were talking about that were input and output. So if we have a machine, so work put into a machine is called input force or input work. Okay, so the work that you have to pedal the bicycle would be the input work, and the output work, the work that the machine does, is called output work. So when the work you do to the bicycle, to the pedals, is the input work, and the bicycle moving you is the output work. So ideally, the input work is smaller than the output work, and we call that efficiency. So efficiency is the output work divided by the input work. And hopefully output work is bigger than input work. So going back to the simple machine, and the guy pushing the box up the ramp, he has to put the input, he pushes on the box up the ramp, and the output is the box moving up the ramp. So he puts in a little bit of work pushing on the box, and then the simple machine, the ramp, allows the box to be moved easier. So the efficiency is how well does the output compare to the input. Similar to that is an idea called mechanical advantage, which we also talked about. This is the number of times a machine multiplies the input force. Another way of saying that is, oops, I spelled number wrong. So, still spelled it wrong. All right, so another way of saying that is mechanical advantage is equal to the output force divided by the input force. So if we look at this wedge, we apply some force. So if this was on an axe, well, we'll just say it's a wedge. If we hammer on top of the wedge, boom, 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 we're applying an input force to the wedge. And then the wedge is splitting this log, so that's an output force. And the mechanical advantage is how much force do you get out based on the force you put in. And the mechanical advantage for the ramp is how much distance can you get based on the force you apply to the box. So hopefully I explained that in an okay way. And I'm double checking that I covered everything that needs to be covered here. I think so. Now, one last thing is that kind of has to do with work and energy is power. Well, this is not the last thing, sorry. Power is the rate at which energy is converted. So typically when we think of power, we think of a light bulb. If you look on a light bulb, it's probably going to have 60 watts, let's say. So that watts is a unit of power. So it converts 60 joules of energy every second. So I'm not going to write that down because, well, we'll go ahead and write it down. So power equals joules per second. So something that uses a lot of power will use more energy per second. Something that does not use a lot of power has less energy per second, less joules per second. So if you go to a hardware store, they're going to have appliances like refrigerators and washing machines. And if you get, sometimes you can buy those appliances that are more efficient and they use less power. So they do the same job, for instance, washing your clothes, but they use less energy to wash your clothes. So they use less power. So that's what power is, simplified. Okay, I promise this is the very last concept. We're going to talk about the conservation of energy. So the idea here is that a phrase you've probably heard is that energy cannot be created or destroyed. So that's energy. You can't make more energy or less energy. You're just getting energy from some other source. Another way of saying that this is the total amount of energy in the universe stays the same. So if we look at all things, all the galaxies and suns and planets, all the energy is you can't make more energy in the universe. Now, when we talk about having more energy or less energy, that's where we talk about systems. So your body is a system. Your body doesn't have all the energy in the universe. So if you eat food, you add energy to your body. So that is, and you can lose energy in your body based on your activities. But the total energy of everything stays the same. That energy you lose gets transferred into some other thing. Usually that's heat. You give off a lot of heat, but you can do other things with that energy also. You could lift a heavy box up some stairs, and now some of the energy you had is now stored in that box at the top of the stairs. So this is a law of nature that is never broken. We cannot add more energy to the universe. So that is the very last thing. Thanks for sticking around. You can share this video, like it, hit the bell icon to subscribe or whatever to my channel. I hope you have a wonderful day full of laughter and joy.